All right, welcome to the deep dive. Today we're going to be diving into something, well, pretty huge, literally. We're talking about liquid cargo handling on ships, those massive tankers that crisscross the oceans. We know you're curious about how these, I guess, behemoths manage to move such staggering amounts of liquid around the world.
It really is quite a feat of engineering, isn't it? When you see these enormous vessels out on the horizon, it's easy to forget the intricate dance of technology and precise procedures that's happening inside, all designed to make sure that cargo gets where it needs to go safely and efficiently. The scale alone is mind-boggling, and the systems they've developed to handle it are incredibly ingenious.
Ingenious is a good word for it. For this deep dive, we've managed to pull together a really interesting collection of material, from high-level system designs down to the nitty-gritty of maintenance manuals. Our goal today, well, we want to break down the core processes and the tech behind moving liquid cargo on these tankers. Make it clear, give you those ha-ha moments, but, without getting lost in the weeds. So to start, let's talk scale. We're not talking about your average tanker truck here, right?
Not even close. To really grasp the challenges involved, you have to understand the sheer size of these vessels. We're talking about oil tankers that range from what they call handy size, which these can carry a respectable 20,000 to 30,000 deadweight tons. And that's already a lot. But then you go all the way up to the ultra-large crude carriers, the ULCCs. Those can carry over 300,000 deadweight tons.
300,000 tons. That's what? Like moving the entire population of a small city in liquid form. It's kind of hard to even picture. So you've got this tanker loaded up. It can't just be a simple matter of sailing across the world and opening a tap, can it?
Definitely not. Handling liquid cargo is a very carefully choreographed process. There are 6 core operations involved. First, there's purging, which is essential for safety. Then, for gas carriers, there's usually a cooling stage. After that comes the loading itself, followed by the long voyage carrying the cargo. Then there's the discharge at the destination port, and finally something called gas freeing the tanks. Each of these stages has to be planned and executed meticulously.
You mentioned purging is critical for safety. Can you explain what that is and why it's so important?
Sure, imagine you're dealing with flammable liquids, right? Before you can even think about loading them, you have to make the environment inside those cargo tanks as inert as possible. That's what purging does. They fill the tanks with an inert gas, something like nitrogen or carbon dioxide, to displace all the air and get the oxygen content down below 8%. This creates an atmosphere where those flammable hydrocarbon gases can't ignite. It's all about preventing explosions, a fundamental safety measure.
So it's like creating a safety bubble in these massive tanks.
Exactly. And for gas carriers, or if they're carrying certain sensitive chemicals, they might even use pure nitrogen for purging. It creates an even more controlled, less reactive environment.
Got it. So even before the first drop of cargo comes aboard, there's a whole bunch of prep work to be done.
Oh, absolutely. Well, before they get to the loading port, every single piece of equipment involved in handling the cargo is thoroughly checked and tested. They make sure it's all in perfect working order. They also run these tightness tests on the cargo tanks themselves. Even tiny leaks are a big no-no.
And it's not just about the hardware, is it? The crew, their understanding of the whole process, that's got to be critical too.
You're absolutely right. The crew has these detail meetings, preloading meetings, where they go over everything. They discuss the specifics of the cargo, its nature, and refer to the Material Safety Data Sheet, the MSDS, which basically outlines all the potential hazards. They go over all the safety precautions, plan out the loading sequence, and also how they'll deballast the ship.
Deballasting.
Yeah, so as they load the cargo, they have to carefully empty water from specific ballast tanks to keep the ship balanced and stable. It's a delicate dance to keep the ship at the right draft, how deep it sits in the water, and prevent too much stress on the hull.
So the ship arrives at the loading port. What happens next? Before and during actual loading, I mean?
Well, the first thing is a really thorough safety check between the ship and the shore terminal. They go through this detailed ship-shore safety checklist together, making sure all their procedures line up and every potential risk is addressed. Then they double-check, really make sure that the inert gas valves on the cargo tanks are open and locked. This keeps that protective, non-flammable atmosphere we talked about consistent throughout the whole process.
Right, makes sense.
And, of course, they test the overfill alarms. Those are crucial. Got to make sure those are working perfectly to prevent spills. The crew also gets a briefing on the specific cargo being loaded at that port. Everyone has to be on the same page, understand the loading plan inside and out.
Okay, so paperwork's done, all the checks are complete, everyone's ready, the liquid starts flowing. What happens then?
They always start the loading really slowly. This gives them a chance to carefully check for leaks anywhere in the system, from the shore connections to the ship's pipelines, right into the tanks. It also confirms that the cargo is going into the right tanks, as per the plan. And they'll take samples of the cargo early on for quality control. Only after everything checks out, no leaks, cargo going where it should, only then do they gradually ramp up the loading rate to full feed.
Sounds like constant vigilance is key throughout the entire process.
Oh, absolutely. The crew is constantly monitoring the liquid levels in all the cargo tanks, not just the ones being filled. They're also keeping an eye on the ship's draft, how deep it's sitting in the water, and the trim, which is basically the angle of the ship front to back. Got to keep the ship stable, minimize stress on the hull. It's really important. And of course, they're constantly monitoring the pressure inside the tanks, making sure it stays within safe limits. They're also in communication with the shore terminal about the venting procedures, making sure everyone's on the same page.
Venting, that's to release pressure or gases that build up as the tanks are being filled, right?
Exactly. And as the tanks get close to full, they start the topping off procedures. The ship will tell the terminal to slow down the loading rate for those last tanks. This allows for more precise filling, helps avoid overfilling. They'll also, where possible, close off master valves to separate different types or grades of cargo within the ship. During this topping off phase, they're constantly checking the ullages.
Ullages,
That's the empty space between the liquid level and the top of the tank. Once the loading is done, they go through a meticulous process of closing every single valve, making sure they're tight, and all the gauging equipment, the stuff they use to measure tank levels, is cleaned and stowed away properly. Then, in many cases, they'll even top up the inert gas in the tanks again before setting sail.
All right, so the tanker's fully loaded, ready to head out. Does the crew get to relax a bit until they reach the destination?
Not really, no. Even when underway, that cargo needs constant attention. The crew regularly checks those ullages in the cargo tanks and makes sure there's a positive pressure of at least 100 millimeters of water gauge inside. This helps keep that inert gas blanket in place, preventing air from getting in. They'll also sound the ballast tanks, basically measuring the liquid level in them every day, and they check the atmosphere inside the tanks too. And of course, they do any necessary maintenance on the inert gas system, boilers, and cargo handling systems during the voyage as needed.
I imagine there's another round of preparations as the ship approaches the discharge port.
You bet. About a day before arrival, they test all the cargo pumps and equipment again. Got to be absolutely sure they're ready for unloading. They also check the alarms and safety shutdown systems for both the cargo and inert gas systems. They'll top up those cargo tanks with inert gas one more time to make sure there's a safe environment for discharge. And if the cargo needs heating, if it's a viscous cargo, they'll warm up the steam lines. For hydraulic systems, they'll circulate the hydraulic oil, get everything primed. And of course, everyone reviews the cargo discharging plan. Got to be crystal clear on all the steps.
A lot of prep work. So the ship's at the discharge port. What needs to be in place before they can start pumping all that liquid out?
Okay, so several critical conditions have to be met. First, all the cargo tanks involved in the discharge, including any slop tanks, holding oil or waste, have to be connected to the main inert gas line. And all the other openings on the cargo tanks, vent valves, sounding pipes, all that closed tight. Got to maintain that controlled atmosphere. The inert gas plant has to be running smoothly, supplying inert gas, keeping that positive pressure. The deck isolating valve on the inert gas line needs to be open. And very importantly, everyone involved on the ship and at the terminal needs to be absolutely clear on the cargo discharging plan.
Sounds like a lot of checks and balances before a single drop is moved.
40 first, always. When they finally start the discharge, just like loading, they begin at a slow rate. This lets them make sure everything is working right, no surprises. Once they confirm it's all good, then they gradually increase the discharge rate. And just like loading, it requires constant monitoring, keeping a close eye on everything. The engineering crew does regular rounds of the pump room, listening for any odd noises, vibrations, checking for leaks, making sure temperatures are normal.
What about the trip back, the ballast voyage, after all the cargo is gone?
Yeah, those cargo tanks might be empty, but they still need attention. The crew keeps checking the liquid levels in the ballast tanks and visually inspects the ballast water surface. Very importantly, they make sure the oxygen concentration in the cargo tanks stays below 5% and maintain a positive pressure inside. Prevents air from getting in, which could create a flammable atmosphere. Can't be careful.
Earlier, we talked about how some cargoes are thick, have high pour points, and need to be heated to flow properly. Can you explain how they do that?
Sure thing. So you've got cargoes like bitumen, heavy lubricating oils, some types of crude oil, even some heavy fuel oils. At normal temperatures, these can be very viscous, almost solid. To pump them, you have to heat them up. They use a network of steam heating coils inside the cargo tanks. Interestingly, the wing tanks, the ones on the sides of the ship, often need more heat than the center tanks to get the cargo to the right temperature and keep it there.
Using steam to heat things up sounds like it could be a bit tricky. Any special precautions?
Definitely. Before they start heating, they make sure the steam lines are drained of any condensate and warmed up gradually. You have to prevent thermal shock to the coils. They also have to carefully check those heating coils for leaks. Don't want steam or condensate getting into the cargo. The deck department, who's watching the cargo, and the engine department, who controls the steam, have to work really closely together, and they have to monitor the cargo temperature very closely. A crucial step is, after they close the steam inlet valve, they always open the drain cocks. This lets any remaining condensate escape, Otherwise, that trapped water can corrode and damage the coils.
Makes sense. So we've talked about the whole process of handling the cargo. Let's get to the pumps themselves, the workhorses that do the actual moving. What are the main types of cargo pumps used on these tankers?
All right, so there are a few main categories. First, you've got positive displacement pumps. Think of these as a controlled squeeze. They move a fixed amount of liquid with each stroke or rotation. In this category, you have reciprocating piston pumps, gear pumps, and screw pumps. They're usually used for smaller to medium flow rates, and they're really good at handling viscous liquids and creating high pressure.
Okay, and what's the other main type?
That would be centrifugal pumps. These are the real workhorses for moving large volumes of liquid quickly. Very common on tankers, especially for crude oil and lighter products where you need that high flow rate. Our sources also mentioned a bunch of other specialized pumps you might find on board, like vertical deep well pumps that sit inside the tanks, submersible pumps that you lower into the cargo, rotary pumps like screw or lobe pumps, stripping adductor pumps for those last bits of cargo, and even dedicated pumps for the inert gas system and tank cleaning.
Let's talk more about those centrifugal cargo pumps. You said they're pretty common. How do they actually work?
Picture a spinning disc with curved vanes inside a casing. That's the basic idea. That disc with the vanes is called the impeller. When it spins fast, it gives energy to the liquid that comes into the pump, right at the center, the eye of the impeller. The spinning flings the liquid outwards into the pump casing, increasing both the pressure and the flow. For really high flows, they often use a double suction impeller. That means liquid can enter the impeller from both sides, doubles the flow.
Now, I know some pumps need to be primed before they can start working. What about these centrifugal cargo pumps?
Good point. Yeah, they're generally not self-priming. That means the pump and the suction pipe have to be filled with liquid before it can start. If there's air in there, the impeller just spins uselessly. That's why they have these self-priming units attached to the pumps. They suck out the air, fill the pump with liquid. Once the pump's moving liquid, the self-priming unit usually switches off automatically.
Smart. What about the design of these pumps? Anything special about them because of their size and what they're used for?
These pumps are often big and powerful, especially on large tankers, so the shaft can be pretty long. To keep things stable, prevent vibrations, these shafts are usually supported in two places by strong ball bearings. These bearings can handle the radial thrust forces from that spinning impeller. Now, where the shaft goes through the pump casing, you need a good seal to prevent leaks. They usually use mechanical seals for that. Very reliable and long-lasting. And here's the neat thing. They often put temperature sensors on those bearing housings. If the bearing temperature suddenly spikes or even gradually increases, it could mean something's wrong. Could be bad lubrication, the pump running too fast, worn bearings, the pump's overloaded, the cargo's hotter than it should be, misalignment, or even some internal parts like wear rings getting too worn out.
So those sensors are like an early warning system. You mentioned vent systems connected to these pumps too. What are those for?
Right, so for the pump to suck properly, we'll talk about this thing called net positive suction head later, you often need vents on the suction side. These vents get rid of any air or cargo vapors that might be the liquid. If these gases build up at the impeller eye, they can mess up the flow, make the pump less efficient.
What powers these big centrifugal pumps?
They can be driven by steam turbines or electric motors. Now, for safety, especially because the pump end can have flammable vapors, the actual drive unit, the turbine or motor, is usually located outside the pump room. Often it's in the engine room, right next door. Power is transmitted to the pump through a shaft, a jack shaft that goes through a sealed opening in the bulkhead, a stuffing box. They also usually have a big, strong thrust bearing at the bulkhead. That handles the axial forces from the pump and the weight of the shaft.
I notice in our notes that the suction head can decrease as the cargo tanks empty. Why does that happen, and is it a problem?
That's just physics. As the liquid level drops, the distance between the surface and the pump inlet decreases, so there's less pressure pushing the liquid in. The inert gas helps maintain some pressure, but eventually, as the cargo level gets low, the suction head drops, and the pump might lose suction.
Okay, let's move on to deep well cargo pumps. These sounds quite different from those centrifugal pumps in the pump room.
They are. You find them a lot on product and chemical carriers, and sometimes on those ships carrying liquefied gases, the LNG and LPG carriers. As the name suggests, they're deep down in the tank, usually near the bottom. They're usually driven by a vertical electric or hydraulic motor mounted above the deck, connected to the pump down in the tank with a long shaft.
And are these also centrifugal pumps?
The principle is similar, but deep well pumps are often multi-stage, meaning they have several impellers in a row on the shaft. This gives them higher discharge pressures, and they typically have single suction impellers. The discharge cargo goes up to the deck through a pipe integrated with the pump column. Now, because that shaft is so long, it needs support. So they use these radial bearings, sometimes called spiders, mounted on brackets within the column. The bearings are often lubricated by the cargo itself, so the materials have to be compatible with a wide range of liquids. And they have to be tough, withstand those times when the pump loses suction during stripping or tank cleaning. For liquids that evaporate easily or have low viscosity, some deep well pumps have a special inducer, a kind of helical rotor, just before the first impeller. It helps with suction and prevents cavitation.
What about submersible cargo pumps?
Yes, those are interesting. We have two main types, hydraulic motor-driven and electric motor-driven. Let's start with the hydraulic ones. You find them a lot on chemical and product carriers, sometimes on crude oil tankers too. One cool thing is you can often have a pump or two in each cargo tank, so you can carry different cargoes without risk of contamination. They're powered by a hydraulic power unit, usually located in the engine room. The pump itself is usually a single-stage centrifugal pump with a single-section impeller, and it's mounted at the bottom of this special triple-walled pipe.
Triple-walled, why is that?
It's a safety thing. The innermost pipe carries high-pressure hydraulic oil down to the motor. The oil returning to the power unit goes up through the second wall, and the space between the second and third walls is filled with air or inert gas under pressure. This pressurized space is a leak detection barrier. If there's a leak in either the hydraulic lines, the pressure in this space changes, triggering an alarm. Prevents contamination, either hydraulic oil into the cargo or cargo into the oil. The pump's rotor is directly connected to the hydraulic motor, supported by ball bearings, lubricated by the returning hydraulic oil. And they have lip seals or mechanical seals to prevent any mixing of the cargo and the hydraulic oil. Any tiny leaks are contained by that pressurized gas, and there's usually a bypass line to collect any leakage. The pump speed and how much cargo it moves is controlled by a valve on deck. After discharge, they can drain the pump and pipe using compressed air or inert gas. And since there's usually no non-return valve on the suction side, they can even use the discharge system for loading by reversing the flow through the pump. They sometimes use these pumps for ballast water too. And the design is such that you can easily remove the pump for maintenance.
And what about the electric motor-driven submersible pumps?
You mainly see those on LNG and LPG carriers. The reason is those liquefied gases are extremely cold, cryogenic temperatures, and regular hydraulic fluids wouldn't work. In these pumps, the electric motor is directly connected to the pump impeller, all in a vertical arrangement. A neat feature is that they often circulate the supercold cargo through the motor housing. This cools the motor and lubricates the bearings before the liquid is discharged. And because these ships carry potentially explosive cargoes, the motors are explosion protected, meeting those strict IGC code requirements.
We also have rotary cargo pumps mentioned in our notes. What are their typical applications?
Rotary pumps, like screw pumps or lobe pumps, are often used as the main discharge pumps, especially for very viscous cargoes that are difficult to move with centrifugal pumps. Sometimes, on ships that primarily use centrifugal pumps, you might find smaller rotary pumps used for stripping. Remember, those are for getting the last bits of cargo out of the tanks. Rotary pumps can be in the main pump room, driven by an electric motor in the engine room through a shaft. Or they could be deep well pumps, with the motor on deck connected to the pump by a long shaft. Either way, the discharge is usually through a vertical pipe up to the deck.
We've talked about stripping pumps a couple of times now. They're the ones used to get the last bit of cargo out, right? The notes specifically mention reciprocating pumps for this. What makes them so good at this job?
Reciprocating pumps or stripping pumps are really important for getting those last dregs of cargo out that the main pumps can't handle. They work by positive displacement, which means they physically push a specific volume of liquid with each stroke. This creates a vacuum on the suction side, so they can actually lift the cargo from the tank bottom. Often they have two pumping cylinders, duplex design, and they pump on both the forward and backward stroke, double acting. Now, to get these pumps primed and working properly, you need enough liquid at the suction, especially if the cargo has high vapor pressure. This prevents vapor locked, which is when vapor bubbles form and block the flow. Keeping their suction lines separate from the main pumps also helps. Sometimes you can improve their performance by closing the discharge valve a bit, which increases the pressure, and by increasing the inert gas pressure in the tanks to push the liquid toward the pump. And if the ship is tilted slightly back, trimmed by the stern, that also helps. With these pumps, you can get the amount of leftover cargo down to almost nothing.
Now, the inert gas system, which is so important for safety, must also use pumps. What kind?
Yes, the inert gas system uses a few types of pumps. If the inert gas comes from scrubbing the exhaust gas from the boilers, pretty common setup, they use seawater scrubber pumps. These are usually single-stage centrifugal pumps driven by electric motors, often arranged vertically. They provide lots of seawater to the scrubber tower where the exhaust gas is cooled, cleaned, and its oxygen content is lowered. Ships with separate inert gas generators, those also need seawater scrubber pumps. And then there's the deck seal seawater pump, also centrifugal. This pump provides seawater to a special seal that prevents cargo vapors from getting back into the machinery spaces through the inert gas pipes. So the whole process is basically taking the flue gas, cleaning it with seawater in the scrubber, removing any water droplets, and then sending it to the tanks.
What about tank cleaning pumps? What do they do?
Sometimes to get the tanks ready for a different cargo, they clean them using hot seawater. This seawater needs to be pumped at high pressure to power those tank cleaning machines, basically rotating nozzles. For this, they have dedicated tank cleaning pumps, typically centrifugal pumps that can handle hot seawater. Then there are stripping inductor pumps. Those are interesting. They have no moving parts. They use pressurized liquid, usually water from another pump, to create suction. This lets them pump out liquids from places like chain lockers, bilges, even cargo holds. Because they have no moving parts, they're simple and can even handle mixtures of liquids and solids.
Now, chemical tankers, they handle a huge variety of cargoes, many of them hazardous. How does this affect their cargo systems compared to, say, an oil tanker?
It's a big difference. Chemical tanker cargo systems are a whole other ballgame. They have to be super versatile and safe to handle all those different chemicals, industrial chemicals, and sometimes even clean petroleum products, vegetable oils, you name it. You often see deep well centrifugal pumps, frequently with hydraulic drives for safety, with one pump dedicated to each tank to prevent contamination. And sometimes they have deck-mounted positive displacement booster pumps, usually screw pumps, to help move those thick cargoes. Their systems are designed for very efficient stripping to get rid of as much residue as possible. They have smooth-walled tanks, often with sloped bottoms for better drainage. And accurate temperature monitoring and closed gauging systems are a must for safety in the environment. And for inerting, they usually have nitrogen generators on board instead of using flue gas.
One specific system we should mention is the Framo hydraulic cargo pumping system. What's special about it?
The Framo system is a really popular integrated hydraulic system for cargo and tank cleaning. The key feature is that it usually has one hydraulic motor-driven centrifugal pump in each cargo tank, but it also includes pumps for ballast, tank cleaning, and even portable pumps, all connected to a central hydraulic power unit. This unit is usually powered by electric motors or diesel engines. The cargo pump in each tank is usually a single-stage centrifugal pump with the impeller high up in the tank. This makes it good for different viscosities and stripping, even when the cargo level is low. For safety, the hydraulic motor and seals are isolated from the cargo by a cofferdam. You can control the whole system, each pump's speed and flow, from a central control room. It also has safety features like automatic power regulation, overload protection, and fail-safe alarms. Special feed pumps ensure the main hydraulic pumps always have enough suction pressure.
What about the layout of the pump room, the piping on deck, and manifold standards? Are there any important guidelines or rules?
Organizations like OCIMF, the Oil Companies International Marine Forum, and MARPOL, the International Convention for the Prevention of Pollution from Ships, set standards for safety and pollution prevention. Some key things are making sure the pipes can flex with temperature changes in the hull movement using expansion couplings, having multiple valves to separate different cargoes, dedicated stripping lines for oily waste, and standardized discharge manifolds that match shore connections. And of course, visual inspections and checklists are crucial.
Now, with all this machinery in a harsh marine environment, wear and corrosion must be a big issue. What are the main causes?
There are a lot of factors. The cargo itself could be abrasive or corrosive. Seawater's always there. You have anaerobic bacteria that can eat crude oil and produce corrosive stuff like hydrogen sulfide, and even high temperatures, especially in heating systems. Piston pumps get wear on piston rings, glands, and valves, while rotary pumps can leak internally because of wear between the moving parts in the casing. The goal of maintenance is to prevent damage, extend the life of the equipment, keep it reliable, and save money by catching problems early.
What does a typical maintenance program for these systems look like?
Well, it includes regular inspections of things like bearings, packing rings, or mechanical seals for leaks, alignment of couplings, looking for erosion or cavitation damage inside, checking clearances between parts, and making sure valves seal properly. It's really important to follow the wear limits set by the manufacturer and keep good records of any replaced parts. Checklists and log files are essential, and troubleshooting charts help diagnose and fix common problems. For centrifugal pumps specifically, they check for both hydraulic problems like low flow or pressure and mechanical problems like high power consumption, seal or bearing issues, vibration, or even broken parts. They also do daily checks, cleaning, lubrication, and leak checks.
What about the Framo system? Anything specific about its maintenance?
With Framo systems, you have to regularly pudge the cofferdam around the submerged pump to check the seals. They also recommend not running the hydraulics at too high a pressure, using the right hydraulic oil and genuine parts, and including portable pumps in the maintenance schedule. You should check the service valves every year, keep the whole system clean, and fix any leaks right away. And in the marine environment, you have to take care of the corrosion protection, like those sacrificial anodes. During major overhauls, it's a good idea to replace wear rings in the pumps to keep them running efficiently.
So we've covered the pumps themselves and their maintenance. What about actually operating them?
Some general rules for installation are: put the pumps close to the suction source to minimize losses, keep the piping simple, make sure the motors or turbines have the right power and protection, give the pump a solid base, and align the couplings perfectly to reduce vibration and wear. When running the pumps, keep an eye on them, make sure they run smoothly and quietly, check the temperatures, watch the power consumption, verify the flow and pressure, and make sure there's minimal leakage from seals. For centrifugal pumps, don't close the discharge valve suddenly. That can cause something called hydraulic hammer, a big pressure surge that can damage things. For tripping with Framo pumps, they usually empty the tank at a lower speed, then purge the discharge line with air or inert gas, relieve the pressure, and then use compressed air or inert gas to push out the last of the cargo. After that, they purge the cofferdam to make sure no cargo leaking to the hydraulics.
You mentioned pump cavitation earlier. What is it exactly and why is it a concern?
Cavitation happens when the pressure on the suction side of the pump drops below the vapor pressure of the liquid. This causes the liquid to vaporize, forming bubbles. When these bubbles move into higher pressure areas inside the pump, they collapse suddenly, like tiny explosions. This can reduce pump efficiency, make it noisy, and even damage the pump, especially the impeller and casing. It can also wear out seals and bearings prematurely.
So how do you prevent it?
The main thing is to have enough net positive suction head available, or NPSHA. Basically, it's the pressure energy the liquid has to get into the pump without turning into vapor. To avoid cavitation, the NPSHA has to be higher than the NPSHR, the NPSH required by the pump. To increase NPSHA, you could design the pipes to reduce friction, avoid closing the suction valve too much, increase the liquid level in the tank if possible, and sometimes slightly close the discharge valve. Also, make sure any air or other gases are vented out of the pump casing.
You've mentioned NPSH a few times now. It seems important. Can you explain it in more detail?
Net positive suction head, or NPSH, is really important for pumps. It's the pressure at the pump inlet above the vapor pressure of the liquid. It's like the amount of push the liquid has to get into the pump. You have NPSH available, NPSHA, which depends on the whole system, and NPSH required, NPSHR, which depends on the pump design. To avoid problems, the NPSHA has to be higher than the NPSHR.
How do you calculate the NPSHA?
You start with the pressure at the liquid surface in the tank, add the static head, which is the vertical distance between the liquid level and the pump impeller, subtract the friction losses in the pipes, and then subtract the vapor pressure of the liquid. If the result is less than the NPSHR, you're likely to get cavitation.
One last thing. We have a warning about positive displacement pumps. What is it?
The most important thing to remember with these pumps is, never run them with a closed discharge valve. Since they move a fixed amount of liquid with each stroke, if the outlet is blocked, the pressure builds up rapidly and can cause serious damage. That's why they always have relief valves on the discharge side. If the pressure gets too high, these valves open and bypass the flow to prevent a dangerous situation.
This has been a fascinating look into the world of liquid cargo pumps. It's amazing how much engineering and careful operation goes into something that seems so simple, moving liquids across the ocean.
Absolutely. What's striking is the complexity of these systems, the different types of pumps, the focus on safety in the environment, and the constant need for monitoring and maintenance to keep things running smoothly.
It really makes you appreciate the hidden world behind global trade. And it makes you wonder, what's next in liquid cargo handling? More automation, new materials, completely new ways to move cargo. It's exciting to think about. Thanks for joining us on this deep dive.